In this video, I will take you through the code and explanation for my implementation of the gradient descent algorithm. We can start by looking at the steps that I will do for writing the algorithm. Firstly, we define a function, and this is done in Python, by the way. Firstly, we define a function from Rn to R that the gradient descent algorithm will attempt to minimize. And if you're not familiar with that notation here, Rn to R, that just means that the function takes in a vector of n variables of real values, and it spits out a real scalar quantity. Secondly, we define a function which will calculate the gradient of the function from step 1 at a point x, and this is the main aspect of the gradient descent algorithm. I'm sure you're familiar with that, where we calculate the gradient at a point, we take the negative of it, and that'll be the steepest descent direction that we take. So it'll be useful to have a formula for this gradient. Thirdly, we create the actual algorithm within a for loop. For we code a termination condition for the algorithm, because you can imagine that if the algorithm gets close enough to the minimum, we might want it to stop, because it might just be pointless to continue it. Otherwise, if it doesn't converge, we want it to stop after some finite number of iterations, otherwise it will continue forever. We also want to code some lines to print out information about each iteration. So alright, let's go over to Jupyter Notebook. So first we import the libraries that we'll use. Alright. Let's look at step 1. Step 1, define a function that the gradient descent algorithm will attempt to minimize. So with this algorithm, I'm going to code it in such a way that it'll be able to take any vector, of any size n, any number of dimensions. It's quite difficult to show examples for higher dimensions, so I'll stick to a small number of dimensions to show the examples. But what we'll do with this function here is we'll just write a simple example function here, which will take in a numpy array and return a float. And what this function will be is just the sum of squares for, let's say, 4 variables. x1 squared plus x2 squared plus x3 squared plus x4 squared. So this function here, it's just x1. How do I write this? x1 squared plus x2 squared plus x4 squared. Alright, so we've done step 1. That is the first step. So the second step is, this one's going to be the most complicated to explain. It's what I found that was quite in depth. And what we'll do is we'll actually vectorize this. So, because we're going to have to, because the gradient vector is a vector of size n, where x is a vector of size n. We could use a for loop, but we'll actually vectorize this. And I'll just show you there you go. So the formula for the gradient, I'm sure you're aware, is a vector of size n. It's just the partial derivatives of x, partial derivatives of f at each of those points, each of those elements, x1, x2, xn. So what it says is how does f change given a small change in x1? And then how does f change given a small change in x2, and so on. So here we have the formal definition of a partial derivative. So you can see that f is a function of x1 through to xn, and each of those partial derivatives, we're just subtracting this value of f at the vector x we're subtracting that from f at the vector x, but delta added to a particular element in x. So this will be undertaken for all the elements in x. So if this will make more sense. If you're not aware of what I mean here, this will make more sense as I code it. Anyways, then we're just dividing by delta, which is this change. And really the definition should be the limit as delta approaches 0. But what we're going to do is we're going to approximate this, and we're just going to use a very small delta. So this is the formula that we will use for the gradient function. This is the true formula. And then it should say the limit as delta approaches 0. So this just comes from the definition of a slope. But in this case, it's in multiple dimensions because we've got the partials here. So these are the steps that we'll do for the gradient function. So we'll vectorize it. In the first step here, we calculate f at just the standard vector x. Sorry, not the standard vector. We calculate f at the whatever x is just given into it. The standard vector actually means something else, so I shouldn't say that. And then we calculate f at this vector x, but delta added to a particular element. And then we calculate that for each j. And then we can calculate the partial derivative of f by just subbing into this formula, and thus the gradient of f. So we can code that in here. So this will take in by array. We set delta to be really small, and it will spit out a numpy array of the same size as x. So firstly, what will be useful is to know the length of x, because you'll see that we're going to have a matrix, and I'll call it the delta matrix, and this matrix will be size n, where n is the size of x, so the same size as x, and on the diagonals it's going to have delta. And you'll see why, but this is going to be then really easy to add to x, and then we'll get this value here. Just this first. There we go. This value here, we'll get that really easily. So firstly, we find the length of x. And then we can perform step 1 here pretty easily. If I go down to step 1. So first we calculate f at the point x. That's pretty straightforward. We just sub it into this function here. So, and then for the step 2, it's going to take a little bit of extra lines here. What I'll do here is I'll just show you what each component of the gradient function does. I'll code it in first here, but what we'll need is we'll call this a delta matrix, and that will just be an identity matrix, but with diagonal equal to delta instead. So if I write down here what that does, if I put an example here, let's say of x is a numpy array of size 4, just whatever it is there, and we say length x with length x. So here I'm just reproducing what's going to be in the function here, just to show you what it looks like. So delta matrix np dot I, and this numpy function here, what that does is just creates an identity matrix of size whatever value you put into there. So we put length x, and then if we print out delta matrix there, we see we just get an identity matrix, but we want to actually multiply that by delta. So multiply that delta there. Delta isn't defined yet. Let's put delta as 0.1. There you go. So we have a matrix with delta on all the diagonal elements and 0 elsewhere. Alright, now that we have this, what we want to do is, I'll print out x just so you can see. So what we want to do is we take this vector x and we add it to each row of this delta matrix. So then we'll get a matrix of the same size as this delta matrix. The first row is going to be 1.1467. Second row is going to be 1 plus 0, which is 1, 4 plus 0.1, which is 4.1, 6 plus 0, and 7 plus 0. And the third row is just going to be like the other two, except 0.1 is going to be added to 6. And then the last row, 0.1 is going to be added to 7. And then what we have calculated then is we have calculated this part inside here. So not the function of it, but just this part here. And we've calculated this for each case, essentially. So this for x1 is in the first row once we've added it. So let me just add it there. So x plus delta matrix. And this is what we've got here. So this for x1 is in the first row. This for x2 is in the second row. This for x3 is in the third row. And then the fourth row, that's for x4. So then that's what we're going to do. So we can write x delta is equal to x plus delta matrix. So then what we want to do, let me just write this here again. So then what we want to do is we want to actually pass that into the function f here, and then we've calculated this for each of those cases, and that's going to be a vector in this case. So what we're passing in here is we're passing in x delta, and remember x delta looks like this. So we're passing in each, well, we want to pass in each of these rows here to f, and each of those rows is going to return one float, which is just f evaluated at those points. Except the problem is, if we supply x delta to x, we get these values. And I mean, this is the size of the vector that we want, but the problem is that these are not the right values. If I print out x delta again, I take the first row, for example. If we supply that to x, or to f, like that. So this here, we want this to be equal to this. But if we actually supply that, we don't get this value at all. So we can see that that's not how the function is working. Like, it's not taking the arrays that we want. And what it's actually taking is it's taking the columns. So if I put the first column here, 1.1, 1, 1, 1, we get 4.21, which is this. So it's actually taking the columns, but we want it to take the rows. And this is an easy fix for this. All we do is just put x delta is equal to np.transpose x delta. That's just going to flip the, if you don't know what transpose does, it just flips the columns and rows around. So this row will go down here, this row will go over here, and so on. So if we go np.transpose x delta, yeah, we can see that that's what it did. So 1.1467, 4.167, and therefore the columns in this case is what we want to put into f, and that works really well because that's what f takes. I'm not sure why f takes it like that. It makes more sense to take the rows, but that's just what it takes.
I'm recording this section just after I finished recording the video because I wanted to just add a part about what actually happens when x delta goes into the function f. So I've just coded this up here, which is basically just what's in the gradient function. And if I run, let's run this as well. If I run this as well, we get fx delta is equal to f of x delta. Now remember that x delta looked like this, and we wanted the columns inside there. And I was saying that the way that it is constructed, the columns are fed into the function, into this function here, f of x. When in fact it's a little bit different than that. It works in a similar way, but for example, if x delta is fed into f here as a numpy array, you can see that each of the components are squared. So if we look at x0, that's actually the row. That's actually the row that's going into there. And likewise, if we look at x1, it's the second row, which might be a little bit confusing, but it works out the same way, because these squareds here, the double asterisk and the 2 that's squared, that performs element wise. On each element it performs a square. So x0 is a numpy array, x0 is the rows, and it works out the same way in the sense that each element of the resultant array will be as if we took the square of each elements in each column. So it works out the same way, as you can kind of visualize it in the sense of each column of this x delta matrix is going in. In fact, it's a little bit different, but the reason that I wanted to say this as well is because when you're playing around with this function, you'll notice that if you did, for example, this expression here, which would have a solution, math.cos. So let's say you put this expression into here, and instead you feed in a 2-dimensional array. This won't work, because when x delta is going into here, and x delta is 2-dimensional in this case. Yeah, so you can see, oh no, hang on, that's not the error. I didn't select it. There we go. So this is the error I'm talking about. Only length 1 arrays can be converted to Python scalars. So if you look at x delta in this case, where you have 1.1, 1, 4 and 4.1 in this example here, if you fed each row into the array, which is what we're doing, and we're putting x delta 0 and x delta 1, and then it's getting fed into the math.cos function, that doesn't work because math.cos takes in a scalar. So if you were to play around with this, then keep in mind to use the numpy versions of the math functions instead, because that's the way it's constructed. When the matrix goes in, each of these indices 0 and 1, it gets converted into a vector, and math.cos, and I'm sure other math functions as well, by math I mean the library math, they don't take in these vectors, but numpy does. So if you perform the gradient descent algorithm, which you'll see in the rest of this video, if you perform it on this function here, it works. It returns a minimum. So, and also, if you were to mess around with some of the functions and try different ones, I find it best to try the 2-dimensional ones. It's just easier to visualize, and it's a lot easier to find an actual example with them. So yeah, keep in mind, if you're adding different functions into here, use the numpy library with the math functions, not the math library.
So then if we do that and put f delta, we get this new array, which this array is equal to this. So this value here, f of x plus delta, for x1 it's this first element here, for x2 it's the second element here, for x3 it's this third element, and fourth element is for x4. So we can write that here. We can say f x delta is equal to f of x delta. And now we have calculated a vector which is step 2, which is corresponding for step 2. And so we have this vector here. This value here is a vector, which is what we've just calculated. This second component here, I'm trying to highlight it, here is just a scalar, because x1, x2 through to xn is just one vector, and therefore it'll just spit out a scalar. So this is just f evaluated at the vector x. So what we want to do is we want to subtract this from each element in this vector here. So by just printing it fx delta. That makes a lot more sense. There you go. So we want to subtract f of x from each of these components here and then divide by delta for each of these components. So if we go f of x delta minus f of x, but we need to define f of x first. So we can go f of x is equal to f of x. So that'll just be, there you go. So that's just 102.21 minus 102, which is 0.21. And we have 102.81 minus 102, which is 0.81, and so on. So then after we've done this, we want to divide by delta. And in this case, delta is 0.1. So there you go. So there we've divided by delta. And yeah, essentially that's what we want to put into this gradient function here, because what we're doing there is step 3. We're calculating the partial derivative of f at the point xj for each of those points. That's why here we get an array of size 4. This one here is the partial derivative of f with respect to x1. This second element here is the partial derivative of f with respect to x2. This one with respect to x3, and this one with respect to x4. And if you remember here, that's exactly what the gradient is. It's a vector of all the partial derivatives. That's what we've calculated here. So we can write that in the function here. Where are we up to? X delta v dot transpose x. Alright, so now we go grad f is equal to fx delta minus fx divided by delta. And we can delete this, all these, because we have a function here. Alright, and that's, I'm just looking at this to make sure that I got it right, but it looks pretty right to me. So there we've calculated step 3, and we've calculated the gradient, so we can return grad f. And there we have a formula for the gradient. And now what we need to do is we look at the steps again for the whole algorithm. We actually create the algorithm now. And we can do that within a for loop. So for I in range, let's just put 100. And I can show you here the update formula. If you're not aware of it, it's just the next iteration is equal to the previous iteration minus the constant here of multiplication, lambda, times the gradient of f. And this lambda here, it's not always a lambda. That's the Greek symbol lambda, by the way. Sometimes it's shown as something else. In machine learning, it's called the learning rate. And there's formulas for actually calculating the optimal lambda or the optimal learning rate. But here we'll just specify it as a constant value. And it will work just the same. So, and the reason that it's minus over here and not plus is because grad f is the calculation for the steepest ascent, but we want to actually go down to find the minimum, so we just take the negative of that. So here we can specify lambda here, and we'll just put it to 0.1. And the algorithm is actually pretty straightforward once we've calculated this gradient function here. So we need to actually specify an initial condition. So in our example, we have 1, 2, 3, 4. 4 n is equal to 4 in our example. So let's put 1, 6, 3, 0. So there's our initial condition. And then we just apply the update formula. what might actually be useful. Grad f is equal to gradient x. There you go. So we've calculated the gradient here, and then we just write that here. And that's it. That is the entire algorithm. So if we print, let's just print the value x here. All right. So this function here, x1 squared plus x2 squared plus x3 squared plus x4 squared, the minimum of that is 0. I'm not sure if that's the only minimum, but it is a minimum. And that just continues, from my knowledge, that just continues for any of these situations. So if you have a sum of squares of elements of the vector, the minimum will just be 0. So this should converge to the minimum 0, and we can test it out by running it. What might be easier is to just round it. So round x to 3. There we go. So if we scroll down long enough, we see 0, 0, 0, 0. And yeah, you can see that it slowly reaches the minimum. So at least it works for this example here. What we can do, well, let's look at the next step. Here you go. Codetermination condition. So we've kind of done that with putting in 100 here, but we can make it more user-friendly by writing end or max iterations. Let's put 200. There you go. So I'll run for 200. Otherwise, we also want it to stop if it reaches some reasonable value. So if it gets close enough to the minimum, we want it to stop, because it might be too expensive or just pointless to go any closer to the minimum if it reaches a certain value. And this could get closer and closer. Like over here it says 0, 0, 0, 0 for all these cases here. But if we don't round it, you can see that there's some slight error. So from my understanding, it won't actually reach the minimum ever. If it's run like this anyways. I'm not sure if there's some ways to actually make it reach the minimum ever, but in this implementation it won't. So max iteration 200. So what we can specify in that case is we can use the norm. We can use the norm of a vector. And why we can use the norm of the vector is that once the gradient, or once the point x reaches close to the minimum of the function, the gradient or the slope will level off. It won't be as steep. And you can imagine that more clearly in 2 dimensions. Like if you envision a quadratic graph, and you can imagine as x reaches the point 0, 0 or gets closer, the gradient and the slope, or the gradient or the slope of the graph will become less steep. And the norm of this will also decrease. So if I scroll down to here, this is the vector norm. For a x vector of size n, the norm of x is just the square root of the sum of squares of each component. And this is what we're going to use as the termination condition, because this will get smaller as the point reaches the minimum. So we can write a end norm. Let's just specify it as 0.01. We'll go 0.001. So here, we actually need to calculate the norm in that case for each iteration. And this is the norm of the gradient, not the norm of x, but the norm of the gradient. So norm grad is equal to, and we can use a numpy function for this, lineage.norm grad f. And that will just be the norm. So what we can specify then is a termination. So if norm grad is less than or equal to end norm, and break. So what this is going to do is, and break, if you don't know what break just means, that just means exit the loop here. What this is going to do is it's going to run through the iterations. If the norm of the gradient becomes less than this value here, it's going to exit. Otherwise, it's going to continue until it reaches the max number of iterations. So all in all, the maximum number of iterations that it can possibly do is 200, but it can do less, if it reaches the norm. All right. So the best way to show this in action is to actually print what's happening here. So first we'll print off just iteration 0. There we go. Just a new line. So then for each iteration, we want to print the iteration number. We print the gradient. Then we print the norm. Oh, actually the norm is not a vector, so we don't even have to use np.round, we just use round. And then we print x. There we go. There we go. All right, so we have an example here. Why is x like that? There we go. All right. So we start with 1630. We see each of the, actually what I'm going to do before I continue, I'm going to put a new line there. There we go. Iteration initial, iteration I plus 1. There we go. So this is iteration 0 here. X initial is 1630. All right. So gradient of f at x, we find the gradient, we find the norm of the gradient, which is above this n norm value, so we keep continuing. And then this is the formula here that's being done to x, which is the same as this here. So this is being done in each of the iterations. And we're just printing out, each iteration here. So we can see that the norm of the gradient gets smaller as the iterations go. And we can see that this x value here, gets closer to the minimum. And we know the minimum in this case is 0, 0, 0, 0. So we can see it's getting closer to 0, 0, 0, 0. And here I put, for the fourth element, I put 0 here. We can see that that's not changing at all. That just starts off as 0 and is 0 throughout. If we put 100 here for the first one, we can see that the absolute value change of each iteration is larger. Like 100 goes to 80, compared to 6 going to 4.8, because 100 is further away from the minimum, so it has to drop a lot faster. So we can see in the end, we can see that we don't actually reach iteration 200, and that's because norm of the gradient here is 0.01. Or it's rounded to be 0.01. Really, it's actually less than 0.01 if we put the norm and round it to maybe 6 decimal places. Yeah, we can see that's much less than that. Or not much, it's less than that. And then, then the loop terminates and we reach the minimum here. If I put more decimal places here, then we can see that this actually won't be the minimum. It won't be exactly 0, 0, 0, 0, and it never will. But we can get closer and closer. And if we run for an infinite number of iterations, theoretically it will approach 0, 0, 0, 0, but it won't actually reach it. So that is the gradient descent algorithm in Python. And you can see that it takes in a numpy array. So the only thing that you need to change here if you want to try different examples, is change this function here, this one here, and then change this initial condition here. You can also change these here, lambda max iterations and end norm, to change the termination condition and also the learning rate if you wish. But I'll give you another example here just before I end. If I go, let's get rid of this comment here, plus x2 times x3. So in this example, we see something a bit strange. The norm is increasing, 1, 6, and it's a huge number as well. So I'm not actually exactly sure why this is the case. I assume that it's because this function here, the minimum can't just be computed normally. Maybe it's not a convex function, or maybe the minimum doesn't really exist at a certain point that makes this algorithm plausible. It's hard to find examples in multiple dimensions for this case, just because multiple dimensions are hard to visualize. What I found is that this algorithm for multiple dimensions, you can always make this algorithm work by just taking the sum of squares, and it will always converge to 0, 0, 0, 0, 0, 0, however many times there is variables. But yeah, from my understanding, the reason that it doesn't work if you do this, for example, is because that function just doesn't work well for this algorithm. I'm guessing it doesn't have maybe a well-defined minimum or something like that. If anyone knows if I'm right or wrong about that, please let me know, because I've been a bit confused about that. But yeah, anyways, this is my gradient descent implementation in Python. If anyone has any thoughts, suggestions, or anything they'd like to say about this, please write down in the comments. Thank you.